Good afternoon, everybody. We are almost at the end of the course of AS level. Yeah. And today we are going to continue with radioactivity, and we will discuss fundamental particles and radioactivity. We start first with fundamental particles. Okay. If I have time, I will make an introduction to radioactivity, but probably today we will only discuss the fundamental particles. In the 19th centuries, we knew there were about, well, more or less, we know there are about 92 elements, and with these 92 elements we can actually make an unlimited amount of different molecules. Yeah? The idea was that atoms of these elements only contain protons, neutrons, and electrons. And they were, protons and neutrons and electrons were actually considered as fundamental particles which could not be subdivided further. However, in the 20th century, they discovered many other particles. Okay? Now, how did they discover the new particles? First of all, by using very sensitive machines looking into the sky and do different types of measurements. Yeah? So they looked actually into the universe and looked at which particles were actually arriving at the Earth. Also, they looked at how are particles behaving, and we were talking about protons, neutrons, if you let them collide at a very high energy collision. Okay? We're going to look in the next video about more or less how did they do that. Okay?
The Large Hadron Collider. It's a massive, beautiful piece of human ingenuity, engineering, and wait a minute, that's not the LHC. This is the LHC. It's a massive, beautiful piece of human ingenuity, engineering, and wait a minute, that's not the LHC. This is the LHC. This is the Large Hadron Collider, or LHC for short. It's a 27-kilometer particle accelerator sitting under the border of France and Switzerland. It's an atom smasher, the biggest in the world, designed and built by thousands of engineers, scientists, and mathematicians from across our tiny planet with the goal of helping other scientists learn about things of incredibly small size by smashing them together. These smashings are called collisions.
This is really all they're interested in. Yeah. They're interested in collisions.
That's Mike Lamont. He's the operations group leader working on the LHC. It's his job to run BEAM. BEAM being nerdy lingo for bunches of hydrogen protons that fill up the LHC. The LHC is a ring containing two beams going in opposite directions. But if we look closer, that beam is actually made up of bunches of protons.
In fact, each bunch has about 100 billion protons each. And these bunches are about 30 centimeters long, typically about a millimeter dimensions as they're going around the ring. And so think about a long, thin, tapered piece of spaghetti.
Incredibly powerful superconducting magnets keep the beams flying at nearly the speed of light with the aim of making these proton bunches hit.
We pass these thin hairs through each other and we get about 30 collisions. So most of the protons just miss each other and they carry on around the ring. They come back one turn later and they can do it again.
And the reason why they miss each other is because atoms are mostly empty space. So getting them to collide is incredibly difficult. It would be like standing 10 kilometers apart and trying to shoot two needle-thin arrows at each other so they hit halfway. So the key is to do this a lot.
The target this year, just to put it in context, is about 800 million collisions a second. So we really have to work hard to get that rate.
Hundreds of millions per second is insane. Imagine trying to control a proton traveling at nearly the speed of light. To keep the bunches on track, the LHC uses dipole magnets, or two magnets. But when they need to steer the protons, they use quadrupole magnets, or four, one on each compass point, applying 300 to 400 metric tons of force per meter.
So we're taking our pieces of spaghetti and focusing down with very strong quadrupole magnets, which are like lenses, to get them down to the diameter of a human hair as we pass them through each other in the center of the experiments.
And that is why the LHC is in the business of collisions. The LHC is sort of like your power company, but instead of providing electricity, they're generating collisions. More collisions, more better. They spend all their effort to try and get these bunches of hydrogen ions to hit inside of other scientists' experiments. Of course, having a collision is great, but if a proton collides in the woods and no one's there, does it make a boson? Who knows? The scientists still have to be watching at just the right fraction of a second to discover a new particle. That's where these experiments come in. They sit on the LHC ring at collision points, and they're probably what you think of when you hear Large Hadron Collider. The famous ones are ATLAS and CMS, which spotted the famous Higgs boson back in 2013.
It's called CMS, compact muon solenoid. However, it really is not compact. It's a relative term, as you can see. Nothing of that size is compact.
Dr. Talika Bose sits in the control room of the CMS waiting for an exciting collision to happen inside her 3-story science experiment, all thanks to the LHC.
So they collide about 25 nanoseconds. So you have a bunch colliding with another bunch. You may have a proton here and a proton here, which has a hard, what we call scattering, a hard event, and out of that comes out a whole mess of particles.
This is what she's talking about. When two protons collide, it looks like this. To you and me, this may look like a whole mess of particle parts, but to Dr. Bose, this mess can actually tell you what's inside a proton.
There are two important pieces of information that we get from this. One is whether it's curving this way or if it's curving that way. That tells us whether it's positively charged or negatively charged, and then how large is the radius of curvature, because it could be curving like this, or it could be curving in a much larger radius, and this has a direct relationship with essentially what the velocity and consequently what the momentum of the particle is.
And this is why the LHC is awesome. Dr. Bose is basically watching millions of proton car crashes in order to reverse engineer the automobile. Smashing atoms together can reveal what they're made of, but instead of injectors, plastic, steel, and glass, physicists find neutrons, kaons, pions, muons, and neutrinos. By the way, physicists call particles that are made of these things hadrons, hence the name Large Hadron Collider. Proton collisions like these help physicists reveal exactly what these tiny structures that make up our universe are made of. The technology is super advanced, but the science is the same as it's always been. We simply break things apart, hoping to understand how they tick. Before we went to the Large Hadron Collider in Geneva, we were on top of planet Earth, 800 miles from the North Pole at the Svalbard Global Seed Vault. To find out what awesome science we were doing there, check out this video.
You know, this is quite simply a hole in the mountain. In there, you have actually 13,000 years history of agriculture.
Okay. Okay, now, at the standard model, normally we were only describing protons, neutrons, and electrons as the fundamental particles. However, due to that high collision of the atoms, of the protons, it's like smashing a car apart, and all particles are flying in a different direction. So we knew that there were other particles inside the protons and the neutrons, and sometimes they make different types of formation. Yeah? So, no longer considers protons and neutrons fundamental particles. Yeah? There are actually smaller subatomic particles. that are found. Yeah, quarks, leptons. Yeah, these are fundamentals. Yeah, and even forces are carried inside particles. Yeah, as I mentioned a little bit about the momentum of a particle. Yeah, okay. All right. Now, families of particles. Yeah, and they are subdivided in two families. Yeah, you might have heard already the hadrons, such as protons and neutron particles, and we call them hadrons because they are affected by a strong force that we discussed before. Then we have the leptons, like electrons. Yeah, these particles are not affected by a strong force. Okay. In this slide, we mainly discuss the hadrons and the electrons. Okay. All right. Let's look inside the hadron. Yeah. The hadron family of particles, they are called quarks. Okay. Now we have like a subdivision into quarks and antiquarks. Very interesting to know. I will show you later also what is the difference in notation. Okay. Now, the interesting is that when an antiquark, they are similar of a quark but like opposite sign. Now, when antiquarks and quarks of the same flavor, talk about that soon, they can annihilate. What does it mean? Actually, they can cancel each other out. Yeah, that's destroy each other. Yeah, that's actually what the word annihilation means, destroying. Yeah. Now, the antiquarks and the quarks, they can be divided in up, down quark, and strange quarks. Okay. We mainly will discuss the up and the down quark because as we find these in the protons and the neutrons. Okay, so again, as I say, pause the video and make some notes. Just another example of antimatter particles. Antimatter particles can have opposite charge or just opposite properties. Okay? And again, as I said, when they meet each other, they can annihilate each other, destroy each other. Okay? Here's an example, and you need to know this example. Yeah, wherein an electron and a positron, which we'll talk about beta radiation later on, when they collide with each other, yeah, they will cancel each other out and then release some energy in the form of gamma ray photons. This is one way wherein radiation occurs. You need to know that, okay? Electron and positron, yeah? A positron is nothing else than same mass of an electron. Electron has a negative charge, complex stands for negative 19 negative, and positron just positive charge. Okay? Okay, let's look at some properties of the quark. Okay? Now, as said, and this is important, you need to know this. Yeah? We have up, down, strange. The charge can be up is always plus 2/3, down is -1/3, and strange is -1/3. If we compare the masses, you will see, this looks familiar maybe, E is mc squared. It's like mass or relative the energy. This is 5 megavolt per c squared. That is meter per second square. The down 10 and the strange 200. Now let's look at our protons. Yeah. Now what do we know about the protons? It has 2 upper quarks and 1 down quark, and the neutron has 1 upper and 2 down quarks. Okay. And most of the mass is in the binding energy. Okay? Okay, let's look at how protons and neutrons are built up. And how do protons get actually their charge? Okay? Now, protons are made up of 2 up, 2/3, plus 2/3, plus 1 down, minus 1/3. So here we see how does the proton get the charge of plus 1. We write it like UUD. Okay? Then we have our neutrons. They are made up of 2 down, minus 1/3, plus minus 1/3, plus 2/3. When we add them up, we get 0. Yeah? And we know that the charge of neutrons is 0, and we call them UUD. Okay? Interesting to know if we have an antiproton. Antiproton. Well, the antiproton consists of UUD, but important to note, to express the anti, we put a stripe on top of it. Yeah? The stripe on top of that is anti. If we have an anti-neutron, we have UDD, and with the stripe on top of that, and that's an anti-neutron. So the antiproton consists of 2 anti-upper quarks, 1 anti-down quark, and the anti-neutron consists of 1 anti-upper and 2 anti-downs. Okay? Just don't forget this notation. Right. And we have some other particles. As you saw already in the video, it's actually quite a jungle of many different types of particles, and many of these combinations of quarks and other fundamental particles. Some of them just can exist for long, very tiny times, because they are very unstable and they break apart again. Yeah. So, and we have another female that is made of 2 strange quarks. Okay. Make a small note of that, and we move on. So again, proton and neutron. Proton plus 2/3 plus 2/3 down minus 1/3 is plus 1. And then we have neutron up, down, down. 2/3 minus 1/3 minus 1/3, and then this. Okay? Okay. I'm going to start to give you an introduction about radiation. Compare a little bit about the difference between alpha, beta, and gamma radiation. And then the next time I will explain more of the different types of radiation equations and which particles are released in the different types of radiation. Okay? Now, the discovery of radiation was done by Henri Becquerel. Yeah? He noticed when a radioactive source is close to a film, it actually affected the film. There was no light. Yeah? So what he did is he made like a special setup wherein a radioactive material like uranium was placed in front of a photographic material, yeah, no light, and he saw that the photographic film was affected by the radiation. Okay, just to know that the unit of radiation is in becquerel. Okay. The detection of radiation can be done by photographic film, or you might have heard it by a Geiger-Müller tube, GM tube. Yeah? And this Geiger-Müller tube is connected to a counter and makes a tick, 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 tick sound. And the higher the radiation, it goes up and up and up and up. You might have seen it in a movie. Okay? And it looks more or less like this. Okay? As mentioned in my previous video, I told you when is radiation going to take place. Now, today I showed you a new example where a positron and an electron, when they are connecting to each other, they annihilate and they radiate out gamma rays. But in most cases, what do we have is we're in atoms. Yeah? When they get too many neutrons, or when they have too many protons, they become unstable and they're going to fall apart, or they give out a radiation in a different form. Okay? So, radiation occurs when an atom is unstable and decays. For example, uranium is going to decay, give off energy, radiation, and some particles. Okay? In the next slide, we will discuss the different types of decay. Yeah? So, what is the main reason that unstable isotopes decay? Remember, the binding energy. Now, when we move up in the periodic table and elements above 83, yeah, they will become more and more unstable because of the amount of protons, and the neutrons cannot anymore add it on to keep them stable. Yeah. Okay. The three types that we know of and you have learned in the IGCSE are alpha radiation. You should know already how they look like, beta radiation, and gamma radiation. Okay? And to finish off this video, we are going to compare the types of radiation. And then in the next video, we will go deeper into alpha, beta, and gamma radiation. Okay? Okay. Let's look at our next slide. Just one note that before I'm going to discuss in short the difference between the alpha and beta and gamma radiation, that we also have beta plus radiation. In the IGCSE, only the beta negative radiation was discussed. Okay. Let's look at the basic characteristics of radiation. Okay? Alpha radiation beta radiation, gamma radiation, positron radiation, or we also can call this just beta plus radiation. Okay? All right. Symbol, you should be familiar already with the symbols. Yeah. Alpha is a helium particle for 2 and has a charge of 2 plus. Beta particle is actually nothing more than an electron with a charge of -1. Gamma radiation has a charge of 0, and the positron particle, or beta plus, is nothing more than a 1 plus electron. So it's a positive. Okay? Yeah? The mass in mu alpha, you could calculate it for a mu. The mass of a beta radiation is the mass of an electron, and it is way less than alpha radiation. Gamma radiation has no mass, just like light, no mass. And obviously the positron is a positive electron, has a mass that is 1/1837. Okay, what is a common source of alpha radiation? Radium, carbon, and cobalt. Then the penetrating power, which we will discuss in each specifically, and why that is. The penetration power is very low in alpha radiation. It will be stopped by a couple of centimeters of air. Beta radiation is moderate. It can go through an aluminium foil. Alpha radiation cannot pass through an aluminium foil. The gamma radiation, the penetration rate is very, very high. Yeah. Yeah. And this can go through aluminium foil or yeah. And positron radiation is very low. Shielding, how can you shield from alpha radiation? Paper, clothing, metal foil, and lead and concrete. You might have gone to the dentist and needed to get some x-rays, and x-rays almost have the same energy as gamma radiation. Yeah, and you see that people are protect themselves when they do x-ray. You have to be covered in a lead, or you go to a special room. Okay. Then the speed. Alpha radiation, relatively slow. Beta radiation, much faster, 10 to the power of 8 meters per second. Gamma ray has the speed of light, that is the fastest. And again, the positron, 10 to the power of 8 meters per second. Okay? Next time we go deeper in the different types of radiation, and you will gain more knowledge than we discussed in the easy physics. Okay? Enjoy your weekend.